Dude, what am I supposed to think though? I mean, I thought you and I had each other's backs. I go away for just a few minutes, and you let pirates show up and take over the lab. What is that? What's the look? Okay, all right. Look, man. You know, it's all good, but man, we gotta have each other's backs here. All right, you gotta be my boy. All right, come on. You got it. All right, all right. I'll see you later. Go ahead. All right, go ahead. All right. That's fine. Well, hey, today we're gonna be talking about solubility and how the K value can help us determine it. Stick around. Previously, we said that in every reaction, at equilibrium, there's a value known as K. It's a constant for that reaction at a particular temperature. So for this generic reaction, we could solve for the equilibrium constant by taking the products, their concentrations, and raising them to the power of their coefficients. And we divide that by the concentration of the reactants, raised to the power of their coefficients, and that's KEQ. We also know that we can take K and learn a little bit about the reaction. For instance, whether or not it's product favored or reactant favored. If K is greater than 1, that means that the ratio of products is greater than the reactants, thus meaning that that reaction is product favored. But if K is less than 1, then we know that the reactant concentrations at equilibrium are greater than the product concentrations, and therefore that reaction is reactant favored. But what if we're not in equilibrium in our reaction? There's actually a value we use whenever the conditions are anywhere else in that reaction process. We call it Q, the reaction quotient. We calculate for Q the same way that we find K. The concentration of the products taken to the power of their respective coefficients and divided by the concentration of the reactants taken to the power of their respective coefficients, just like we do for K. And remember, we're talking about the conditions anywhere in that reaction process. It may or may not be at equilibrium. So how does Q compare to K? Let's find out. Let's say that this diagram represents the extent of our reaction process, the whole spectrum. And right here I put equilibrium. This is K. Remember, K represents the conditions at equilibrium. So let's say we take some samples during the reaction of our reactants and products, and we find that when we calculate for Q, Q is less than K. If Q is less than K, it means that the reaction has not gotten to equilibrium. And so the reaction is going to proceed to the right, toward equilibrium. If we take samples and we find that Q is greater than K, that means the reaction is going to progress to the left, back toward equilibrium. Now let's get back to discussing our topic of solubility and how it relates to K. This beautiful yellow substance inside the flask is lead iodide mixed in water. However, as you can see, it is not mixed very well. Do you see all that solid at the bottom there? I've allowed it to settle out. Before, it was all together like that. So what's happening in this process? Well, some lead iodide is indeed dissolving into that water, but not much. Here's the reaction that's taking place. Lead iodide solid, and by the way, it's lead 2 iodide. Lead has a +2 charge here. Lead 2 iodide solid dissociates to give us ions of lead 2 and 2 iodide ions in solution. But here's the thing. When I start putting lead iodide solid into this water, as soon as I start forming ions, that reverse reaction starts happening, where those ions start reforming lead iodide. So I have this battle going on of dissolving or dissociation and recrystallization happening. And when that happens, when we get to the point of equilibrium, we find that very little ions are formed in the process. So because of that, we can use K in the same way with this reaction. In fact, we find that K is very, very small for this reaction. Why? Because there are so few products, so few ions compared to the reactant, the undissolved solid. The K value for this reaction is 9.8 times 10 to the negative 9th. Wow. So remember, when K is less than 1, that means that this reaction is reactant favored. And boy is it ever in this case, isn't it? Because we have, at equilibrium, very few ions in that solution compared to undissolved solid. When we use K for this purpose, we call K KSP, the solubility product constant for this reaction. And we can calculate KSP the same way that we do for K in a regular reaction. That is, we take the products taken to the power of their respective coefficients divided by the reactants taken to the power of their respective coefficients. So for this reaction, the KSP would be the concentration of lead-2 ion multiplied by the concentration of iodide ion to the second power divided by the concentration of our reactant, PbI2, lead-2 iodide, to the first power since there's no coefficient. But wait, lead iodide is solid. Remember what we said about solids or liquids? They're pure substances. We don't use them in our KSP expression. And so therefore, our KSP is just the concentration of lead-2 multiplied by the concentration of iodide ion to the second power. So that's our KSP for this reaction. And for reactions where you're dissolving a solid, that's usually going to be what the format looks like. Here's some other examples of dissociation reactions. Here's magnesium carbonate solid dissolving to form magnesium ion and carbonate ion. Magnesium is a +2 ion, carbonate's a -2 ion. And so our KSP would be the concentration of magnesium ion times the carbonate ion. Incidentally, this has a KSP value of 6.8 times 10 to the -6. Now, again, that's very, very reactant favored. What about this one? Calcium hydroxide solid that dissociates to give us calcium ion +2 charge and 2 hydroxide ions with a -1 charge each. So the KSP here would be the calcium concentration multiplied by the hydroxide concentration to the second power. Again, because our coefficient is 2 here. It has a value of 5.0 times 10 to the -6. Again, very reactant heavy. What about this one? Wow, take a look at this. Calcium phosphate, Ca3PO42, which dissociates to give us 3 ions of calcium with a +2 charge each, and 2 ions of phosphate with a -3 charge each. So the KSP we would write this way. The calcium ion to the third power, because there's 3 calciums going on here, you see that? Multiplied by the phosphate concentration to the second power, since there's 2 phosphates that come from each of these solids. Now, make sure when you do this that you don't get confused with the charge and the power. Okay? Remember, the power comes from the coefficient in front of each of these ions. 2.1 times 10 to the -33rd. Wow, that is extremely hard to dissolve. You're not going to get much in the way of ions at all from this. Now, is there a way to figure out what the concentration of these ions are in 1 liter of water? Let's say we tried to dissolve some into 1 liter of water. How much of these ions would be present? What concentration would there be based on this KSP? Is that possible? Of course it is. Let's show you how. Now remember, each lead iodide is sort of like this marker I have here. When one of these dissociates, it dissociates into a lead and 2 iodides. Okay? So because of that, I'm going to get X amount of lead in each lead iodide, and I'm going to get 2X amount of each iodide. You get it? So here's what I've done. I've set my KSP equal to 9.8 times 10 to the -9, the actual value of this reaction. So I'm substituting X for lead and 2x for the iodide. One more thing, I still have to remember my exponent of 2 for the iodide, just like I did before. This is just using the concentrations of each at equilibrium. Does that make sense? So remember, for every lead iodide I get into the water, it breaks apart to form a lead, X, and iodide, 2X. So now we can figure out the concentrations with a little math. What? Your markers don't have two caps? Okay. So now when I take X and 2X squared, I get 4X cubed. You get that? 2X to the second power would be 2 to the second power, 4, and X to the second power, X squared. Multiplied by another X, and I get 4X cubed. That is equal to my KSP value, 9.8 times 10 to the negative 9th. So now I divide both sides by 4, and I get 2.45 times 10 to the negative 9th is equal to X cubed. I take the cube root of each side, and I get a value of X of 1.35 times 10 to the negative 3rd. Now remember, that is my lead value. That's the value of my concentration of lead. So lead is equal to X is equal to 1.35 times 10 to the negative 3rd moles per liter. And the concentration of iodide is twice that, 2.7 times 10 to the negative 3rd moles per liter. You see, we can do it. We can also use KSP to determine if a precipitate will form when we put two solutions together. Let's take this example. Equal amounts of 0.01 molar NaCl solution and 0.02 molar lead nitrate, 2 nitrate solution are added together. Will a precipitate of lead 2 chloride form? Now the KSP of lead 2 chloride is 1.7 times 10 to the negative 5th. So how do we do this? Now notice that the ions we need are in both of these solutions. The chloride will come from the NaCl solution. The lead 2 will come from the lead 2 nitrate solution. And you'll notice that I've written QSP up here. Remember Q from earlier? We don't know that we're at equilibrium with these conditions. So we have to assume that we are somewhere in that reaction. So we're going to use Q instead. Once we solve for Q, we can compare it to the K value, the known K value of this reaction. If Q is less than K, no precipitate. But if Q is greater than K, we'll get precipitate. First, let's find out the concentrations of each of these ions. So since we mixed these two equal amounts together, that means the concentrations of each one is cut in half. You get it? We went from one volume to double the volume. So that makes the concentration half as much of each one. So we find the concentration of lead then by taking the concentration of lead 2 nitrate and dividing it by 2, which gives us 0.01 molar. We find the concentration of chloride by taking the initial concentration of the salt solution, dividing it by 2, since we're now double the volume, and we get 0.005 molar. So now we can take these concentrations, plug them in here, and solve for QSP. Okay, so we've plugged into our equation 0.01 multiplied by 0.005 to the second power, and we get a value of Q of 2.5 times 10 to the negative 7th. So what about it? Do we have a precipitate forming or not? The answer is no, we did not. Since Q is less than K, no precipitate. So there you go. That's how we know if a precipitate forms or not based on the KSP. Now one thing it's important to note about these KSPs, over the years, as they've been developed as being accepted values, they do it at 25 degrees Celsius. So all these KSPs that we're using are KSPs of that reaction at 25 degrees Celsius. Now, let's take a look at two beakers I've drawn on the board here. One has a liter of pure water. The other has a liter of 0.1 molar potassium iodide solution, aqueous potassium iodide. Now, this KSP value means that in 1 liter of water, I can dissolve that many moles into that liter at 25 degrees Celsius. So I've done that in our experiment here. I've taken 9.8 times 10 to the -9 moles of potassium iodide, and I was able to dissolve it in this liter of water without it precipitating. And I would be able to if I could do that. However, when I do it in the second beaker, the one that has the aqueous potassium iodide solution, I put 9.8 times 10 to the -9 moles in there, a precipitate forms. Why? It's because of something that we call the common ion effect. In this case, we already have one of the ions present, the iodide ion, is already present in this beaker. And we can answer this with the Le Chatelier principle.
Who goes there?
Oh boy, not him again. Tell you what, let's see if we can do this without him, all right? So, Le Chatelier principle tells us that if we add products, right? If we add products to this reaction that's in equilibrium, that reaction will do what? It will shift back to the left. What's on the left side? The solid. So by adding the exact amount that we can get into 1 liter of water at 25 degrees Celsius into this beaker, it was too much because we already had some of that ion available to us. So again, in this example, the iodide ion was a common ion, one between potassium iodide and lead iodide. So because of that, it shifted the reaction back to the left, where we have solid lead-2 iodide, thus making a precipitate form. Okay, so earlier in this video, we did a solubility problem. We solved for the concentrations of lead-2 and the iodide ion in a 1 liter solution with the KSP. Remember that? You can go back and take a look at it again. So here's your problem. I have copper 2 carbonate that dissolves to give copper 2 ion and carbonate ion. The KSP for this reaction at 25 degrees Celsius is 2.5 times 10 to the -10th. So, based on what we've talked about with KSP and how to figure out KSP, calculate the solubility. In other words, the concentration in molarity, moles per liter, of the copper 2 carbonate at 25 degrees Celsius. So, you're finding out the concentration of copper 2 ion and the concentration of carbonate ion. See if you can do it. So that's the end of the video for today, and it's the end of the videos for the chapter. Wow, here's another one in the books for us. Great job, guys. What did we learn today? Well, first we talked about KEQ again, just to remind us of how to figure KEQ from a given reaction. Then we talked about Q, the reaction quotient, how that can occur anywhere in the reaction, and so we can find Q based on the concentrations of the reactants and products anywhere in that reaction. So if Q is less than K, it means the reaction is still proceeding toward equilibrium. If Q is greater than K, it's proceeding back toward equilibrium. And if Q equals K, you're at equilibrium, aren't you? Remember that. If Q equals K, you're at equilibrium. We find Q the same way we do for K. Then we talked about KSP, the solubility product constant, and how we can determine that based on a reaction. Finally, we talked a little bit about how we can use KSP to determine if a precipitate will form, and in that we included the common ion effect. Now, if you already have an ion present, it may cause you to have a precipitate because the reaction pushes back toward the solid. I hope it's been informative to you as always. If I can help you in any way, shape, or form, please give me an email. I'll be happy to help. Until I see you next time, God bless. Why
like my dog, my hombre.
You're doing a terrible job. Terrible job. You can't call yourself security no more.
We've had a lot of people making complaints about your ability to be a security guard, okay? A lot of complaints. A lot of people have been talking about it.
It was then Slim thought about where he had gone wrong. Slim realized he had made some poor choices, that things had gone wrong, mostly because of his own undoing. Where would he go now?